Hello everyone, my name is Samhan Sachai. I would like to explain the poster you are seeing here, Transparent and Interpretable Control by Reinforcement Learning Agents, an empirical study on linear function approximators for isolated intersections. Let me start from number 1, background. Reinforcement learning is a machine learning paradigm that can be used to solve sequential decision-making problems, such as urban traffic signal control here. So in RL, we have an interaction between agent and environment repeatedly. So in one interaction, agent is taking its action, sending the signal of action to the environment, and this in turn displaces the agent into a new state along with a reward signal, telling whether its action in the former states was good or not good. So it can learn from the reward signal, so-called. So in nowadays, value-based our agents are mostly represented by sophisticated or complex function approximators, mostly artificial neural networks or sort of artificial neural networks. The problem is that their parameters are too numerous and cannot be interpreted. And so comes the research question. So could an RL agent that are using the simplest linear function approximators reach the same performance level of those using more complex function approximators? So the functional form that we are trying to experiment whether it's working or not is the simplest, the linear one, in contrast to the ANN. Following this research question, we go to number 2. A control problem is set up. This is a control of a simple two-lane roads intersection with no turning base. Total vehicle arrival rate is kept at a moderate level so that it is certainly far from the saturation level. Also, a detection system set up, and the scope of this detection system is 100 meters from the stop line. This is used in the modeling of sequential decision-making problem, formerly called Markov decision problem. So the definition of states, reward, and actions are given here. So states is a concatenation, here a concatenation of lane, queue length, and one hot encoded active stage. Reward function is simply the same information, but summed together to form one scalar. And discrete actions is simply, there are two possible actions: to give green for the north-south direction or to give green in the west-east direction. And each action is done every 10 seconds in the simulation. Next, let me go to number 3. So proposed techniques and experiments design. As we are using linear function approximator, there are several benefits. These two techniques are exploiting the characteristics of properties of linear function approximator. Number 1 is that we can set the initial weight value to be something that is logical. I call this informed initial weights. So how this is logical? If you take a look at this matrix, the weight matrix, the column is corresponding to the action, and the rows are corresponding to state features. So there's logical relationship that we know already. For example, if we have Q in a west approach, so the better action to take is to give green in the respective direction. For example, the second technique that we can do is to use least square solution instead of stochastic gradient descent. So this can be much more data efficient compared to stochastic gradient descent. And to benchmark this linear function approximator, an artificial neural network is also set up for comparison. And this ANN artificial neural network is one with only one hidden layer. That hidden layer is composed of 32 neurons. And to the right-hand side, table of experiment is displayed. So starting from experiment number 1, ANN is used. And of course, if information weight is not possible because it cannot be interpreted each individual parameter. And the only learning method possible is, of course, the stochastic gradient descent. And following experiment number 1, so number 2, the subsequent one, only one of these is changed. So we change it from ANN function approximator to linear function approximator. The remaining is kept the same. From number 2 to number 3, only one is changed, which is the information weight. This is the first experiment where this is introduced. And similarly, from 3 to 4, the learning method is changed from stochastic gradient descent to least square solution. And number 5 is rather special. It is doing actions based on just the informed initial weights only. So let's see the results. So in number 4 here, I have summarized the performance of learning in 2 matrices. The first is intersection throughput, and the second is mean delay. So the first metric, intersection throughput, is fundamental, meaning that it should be able to process all the vehicles generated to the intersection. So if we see from experiment number 1 to 3, the plots on the left-hand side, we can see that agents in the experiment number 1 and 2 are not doing that well. It cannot process all the vehicles, and as learning continues, it converges to the performance level of experiment number 3, agent from experiment number 3. On the other hand, the agents in experiment 3, 4, 5, they are using information weights and almost perfectly processing all vehicles, so that the matrix of throughput is already satisfied from the beginning of learning. So no need for learning to improve in this aspect, actually. And if we shift to see the performance in terms of mean delay of vehicles, this is in accordance with the previous metric. So in the experiment number 1 and 2, the agents are not doing very well in the beginning, and it tries to converge to a better policy, resulting in a lower mean delay as learning progresses. However, if we go to see the plots on the right-hand side, we might be suspicious that, okay, using informed initial weights are already so wonderful, so amazing, but do we still need learning? The answer is yes. If we take a look at experiment number 3, it is slowly descending to a better optimum of control performance. And if we see the agent, the result of agent from experiment number 4, it is quite good already from the beginning. A few iterations of training only, it is significantly or obviously better than non-learning agent from experiment number 5. So in conclusion, here we can conclude that using the linear function approximator can reach the same performance level, and each individual parameter can be interpreted because we have direct logical relationship between the input and output of function approximator. And through this transition from complex ANN function approximator to the linear one results in a substantial decrease in number of weight parameters. And lastly, some techniques that are proposed and demonstrated here can be used to accelerate learning, to make learning much more efficient. And this is all of my presentation. Thank you very much for your attention.